Hi, welcome to section 11.7, the ratio of areas. Our objective for tonight is to find the ratio of areas by calculating comparing areas and by applying properties of similar figures. For our homework, we're going to be working on page 546 to 549, numbers 2 to 18, the evens. So let's go ahead and let's get started right away. We're going to find the ratio of the areas of the parallelogram to the area of the triangle. Now, if we want the ratio of the parallelogram to the triangle, we want to make sure that the parallelogram is going to go on top and the triangle is going to go down below. So here we go. Area of the parallelogram is of course going to be base times height. Area of the triangle is of course going to be 1/2 base times height. So let's go ahead and plug in those pieces. Base of my parallelogram is 9 times height of my parallelogram, which is 10, is going to give us 90. For that triangle, 1/2, my base is going to be 12, my height is going to be 8. Half of 12 is going to give us 6 times 8, which is going to be 48. Now we want to make sure that we're going to reduce that fraction. Both the top and bottom are divisible by 6. 90 divided by 6 is going to give me 15. 48 divided by 6 is going to give me 8. It doesn't reduce anymore. We can either leave it as a fraction and don't change it to a mixed fraction, or we can write it with a colon in between. Either option is going to be good. So here's our next example. In the diagram, AB is 7, so I'm going to mark it in. BC is 5. We're going to find the ratio of the area of triangle. Let's go over this. ABD to triangle CBD. Okay, so here we go. We don't got a lot of information here. Here's what we know. I have the base of my first triangle is going to be second. The base of my second triangle here is going to be 5. Now I want us to think about this. We know area of the triangle is going to be 1/2 base times height. I'm going to go ahead and draw in my height for that first one. Now, I can't assume that any of my angles are special angles. We don't know 30, 60, 90s, 45, 45, 90s. We know nothing. Let's go ahead and I'm going to pick the color pink. And I'm going to draw in the height for my second triangle. Now, the height for my second triangle, if I'm using base 5, my height has to start from a vertex and drop straight down. It's going to be the exact same height, only formed with an extension of the side, which as we know we never use in our area formula. Now, if we have two triangles that have the same height, but different bases, what do we know about it? Hopefully you're thinking to yourself here, well, if they both have the same height, but different bases, I can maybe try and plug it into a formula. Well, let's go ahead. Let's just call our height here x. So we have the area of this orange triangle, the first one listed, is going to be 1/2 of 7 times x. The height of the second triangle, which I have outlined here in yellow, is going to be 1/2 5 times x. So as we see, those 1/2s are going to cancel out, and those x's are going to cancel out, and actually the ratio of my sides becomes the ratio of my area, since we have the exact same height. So we're going to have 7 to 5, or 7 to 5. Either way you want to write it is good with me. So this brings us to our first theorem. Our first theorem states, if two figures are similar, then the ratio of their areas equals the square of the ratios of the corresponding segments. It's called the similar figures theorem. Now, the name of it isn't important, but the application is. So if we want to find the area ratio, the ratio of area of figure 1 to figure 2, as long as we know we have similar figures, you can take one of our sides and square it over our other side and square it. So let's go ahead and let's mark this up here. Let's say that I have two triangles that are going to be similar by angle. One big triangle and one little triangle. But it's either stated as being similar, or we can use one of our 3 postulates in order to prove that they're similar. If we match up corresponding sides, let's say this triangle has side 7 and this triangle has side 2. As long as our figures are similar, if we write out our similar corresponding sides as a ratio and we square them, this is going to be the ratio of their areas. 49 7 squared to 4 2 squared. So let's see if you got this concept. We're given similar triangles. Not only are they similar, but we can also see the tick marks. I want you to find the area of their ratio of their areas. Alright, so here we go. If I set up my sides as a proportion, we have 4 over 6. Before I even square those, I want to reduce them. I'm going to get 2/3. Now, once I have my similarity for my sides, I'm going to square it from there, which is going to give me 4 to 9 as my ratio. Now, let's say I didn't reduce it first. If I squared it from here, I would get 16 to 36. Both top and bottom are going to be divisible by 4, so it would end up giving me the exact same ratio of 4 to 9. We would just have to reduce with bigger numbers later. So here's our next one. We're given similar pentagons as shown. Find the ratio of their areas. Press pause and let's see what we got. Hopefully, you did 12 over 9 and either squared it from here, or what I would have done was reduce it. It would have reduced to 4 to 3. Square top and square the bottom, and that's going to give me a 16 to 9 ratio, or we can write it 16 colon 9. Both answers are perfect, and hopefully we're getting the hang of this. Alright, now let's work backwards. If the ratio of the areas of two similar parallelograms is 49 to 21, find the ratio of their bases. So let's think about what we did. When we knew the sides, we squared them once it was in reduced form to get the area ratios. So let's work backwards. We know our area ratio is going to be 49 to 121. We want to think if it reduces, but it doesn't. Now, we have to work in reverse. Instead of squaring the sides, we have to go backwards, and we're going to square root those areas. So here we go. Square root of 49 is going to give us 7. Square root of 121 is going to give us 11. So the ratio of their bases is going to be 7 to 11. We just got to work backwards. We're given that AM is the median of triangle ABC. Find the ratio of the area of triangle ABM to the area of triangle ACM. I want you to think through this logically. Push pause and let's see what you got. Now hopefully here's what we're thinking. We're thinking that a median hits at the midpoint, creating two equal segments. Now, let's highlight over those triangles. We have triangle ABM, which is going to be my first one in yellow. Let's do my other one in this kind of creamy kind of color. We have triangle ACM. So let's think about this. Let's go ahead and let's draw in our heights here. The height for that first triangle, my yellow triangle, if this is my base, side BM, my height is going to be an external height. It's going to mean outside with an extension of my side, which again does not get used in my area. Well, look at this kind of creamish color. We have triangle ACM. Its height for base CM would be the same height. If we have the same base and the same height, that means we have the same area. So the ratio is going to be a 1-to-1 ratio. Now here we go. Last slide that we're going to have here is going to talk about a theorem that we have associated with this. That theorem states a median of a triangle divides the triangle into two triangles with equal areas. Hopefully that makes sense to us. If we have the same base because it was bisected full side, and the same heights, same base, same height, same area. So here's the answers to our homework. Again, it was numbers 2 through 18, the evens. Work your way through this. Make sure we understand these concepts. If you have any questions, please let me know. And as always, let's have a good one.